Hello everyone, it's time for class again. This is ECE341, the probability and the random process course. ECE341. This is a 14-week Wednesday's class. Alright, today the last class with new material. Then Friday we will have a review, then we will need to prepare for the final exam. Right? Okay, today I will just want to introduce something related with the statistics. Actually, I have the homework here. We have this homework, right? Homework problem of statistic part. Suppose you have some date, like the first problem, right? Suppose you have some date. Usually, this is what can you have during a statistic work, right? You want to estimate something based on the observed date. You do not have something else like the distribution, the probability. No, you do not have that. You only have these observed date. And then you want to do some estimation, like you estimate the value of some parameters. But every estimate, before you start to estimate, you need an assumption. You suppose X, a base kind of a distribution, like in these homework problems, we have suppose they are normal distribution or uniform distribution, exponential distribution, Gaussian, that means normal, right? You suppose they have this kind of distribution, then you can estimate the related parameters. But now I have a problem here. Why you think they obey like a Gaussian distribution, or you think this data related with a uniform distribution? Why you think that, right? Why you give this assumption? So actually, before you give this kind of assumption, before you give these assumptions, you need to do some observation on this date. You need to check this date to make sure, okay, this date most possibly it looks more like a Gaussian distribution or a uniform distribution. Then after that you do the estimation. So I have two problems. One is how to check the distribution, how it looks like. Why you can see this obey some kind of distribution. The other side is we have some common used distribution. What are the density function looks like? Right? What are the density functions? How do they look like? This part is somehow easy. So here, let me, ready. So first things, the graph of PDF of some distribution. We have this distribution in the textbook. Textbook Appendix A. Appendix A. Yeah, this is the end of the last part of the textbook. Appendix. Appendix A. There are some families of random variables. Oh, they do not have picture. I want some picture of the. They have the formula. They have the formula, but they do not have the picture. Anyway, we can see. We can find them from. We can also print draw the graph using MATLAB, but here I think internet they should have that. Go to the base. Like the first one, of course, is a normal distribution, right? Normal distribution. Yeah, they have graph here, right? This kind of things, normal distribution. Like a normal distribution. You see that in mu sigma squared mu sigma squared, then the graph will look like this way, symmetrically, and the center located at mu. It's like this. This is PDF, fx of x. This is a normal distribution. This one, right? Normal distribution. And that beta distribution, here's a beta distribution, beta ij, right? Beta ij. And we can have beta distribution. Beta distribution. Okay, see. It's like this. They put them all together. The things like that. The beta. Beta I and j. Depending on the parameter, they can have things like from 0 to 1. So this one, the sample space must be run from 0 to 1. Then it will be something looks like this, or looks like this, or like this. Depending on the I and the j. It's a curve. Start from 0, then increase to some peak value, then going down to 1. Just one peak. And the peak location of the peak, depending on the I and the j, maybe the left side close to 1, or maybe right side close to 1, or maybe left side close to 0. If I and the j are same, then the graph will be a symmetrical one. This is a yes, this is something like this. This is I equal to j. Yeah, depending on I and j. I and j, like both are 1, both are 2, both are 3. The curve is also different. Yeah, some curve like here. It also run from 0 to 1. The sample space is always 0 to 1. This is beta distribution. This is also PDF. It's PDF. And we have something else, like some common used distributions, like the Cauchy distribution. In statistics, we have several distributions. They are commonly used. Gamma. I think the gamma maybe is one. Yeah, gamma. Well, they're gonna have. Anyway, we will check online. Yeah, gamma is one of it. You can see gamma firstly. Gamma, then we have chi square, we have f, we have t, chi square. The gamma firstly. Gamma distribution. Now we go to image. Oh, they do not have a formula. Okay, just go back. Gamma distribution Z. Gamma distribution. Right. Gamma distribution. They also have two parameters. Right? Two parameters. See the graph. It has two parameters. Distribution. Gamma with two parameters, k and p, k and z. Then the graph might be like this way, right? Like this way, or like this way. Right? So it's like this. Yeah, these kind of things. For different k and z. Okay, and the side, the sample space. They will go to infinite. I think. Yeah, just 20. You can go to infinite. Yeah, depending on the graph, or they gave like some graph gave until 3, here's until like 1,000. Yeah. So the sample space for not just 0, 1. It will be infinite from positive sign or positive sign. And the gamma distribution, we also have F distribution. F distribution, just F distribution. F distribution. Yeah, F distribution. F distribution. Let me see, D. F distribution. They also N and M, 2 parameters. There is something looks like this one, like this one. Right. And more, actually more, I just put it here. Is a chi-square distribution, chi-square distribution. T distribution. Let me see, Ft, chi-square. Yeah, most common use, you know. Actually, in statistics, most common use, we have the normal distribution, F distribution, chi-square, and T distribution. These 3 are most important, most common used. Put the star here, most common used. Of course, normal is among all of them. This is the most useful one. Right. Okay, then you can compare your data with these distributions. You can compare your data with these distributions. Then you make a decision. Okay, what kind of distribution I can suppose it is, and then what kind of parameter do we want to estimate? Right? And for to check that, remember that we have this in some early course in the, I think in the first week's Friday. First week's Friday's class of this semester, or maybe the second week's Monday's class. I think it's Friday's class. Yeah. I have introduced a way to see how to estimate the probability from the observed data. Now we can observe some data, but we can estimate more because actually we know more about the whole theory, right? About the probability distribution, the all kind of average values, right? Here, let me do some examples. Let me go to here so I can save the code for the edit. Nice. Okay, edit. This is lecture 14, Wednesday's lecture. So I put the code inside here, and I will put this in Blackboard. Okay, in case someone interested, you can have a look. Alright, here I give a x, just x. X is a x1. It's a random. For example, random. I gave this is sign 1 and 2000 date. Alright, I have a x1. This one we know. This is the building function of MATLAB. It will give a uniform result between 0 and 1. Right? So you can see you this one to see x1 how they look like. Right? Save. Okay, then let me run it. F5. Okay, you see. Yeah, this is the histogram. So what we'll do is, okay, second. Let me write here. You check the histogram. 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 Histogram of the observed date. Yeah, check the histogram, and then compare with some distributions. Yeah, then you can suppose, then make a guess, like guess the date is coming from coming from certain distribution. Yeah, so you can do like this. So here, like in this example, yeah, we know this is a uniform distribution, and then I check the histograph. It looks like almost a straight line, right? So you think, okay, we suppose it is a uniform distribution. That makes sense, because uniform distribution, there will be straight line. Or uniform distribution, right? Uniform distribution. I didn't put it here. Yeah, uniform distribution. It's just a straight line, right? It's straight line. So you can do that kind of assumption. Okay, now let's do some change. If I have another one, x2 is also a random 1 and 2000. And x3 is also random 1 to 2000. Now I have three different random variables, and I let y equal to the average, summation, just a summation. Okay, x1 plus x2 plus x3. Then how about this y? What kind of distribution you think it will be for this y? Okay, we just try to run it. Oh, it looks like this. So which kind of distribution can you imagine? You can think, okay, I just assume this distribution is a kind of like for example, you think it's a normal. Yeah, we have several choice, like several possible choice. Right? You can think it is a normal one. You can also think it's a beta with I equal to j. Or actually here, like a t distribution is also symmetrical. You can also think maybe it is a t distribution. Right? Yeah, that's your choice. You can choose different distribution and make your assumption, and then start work based on that assumption. Of course, the most common used one, people like to use normal for this kind of things. This is symmetrical. Okay. Now I make a change. Like I use x1 plus x2. If here is a square, I put a square here. Alright, then what will happen? I put it 2 times. A little bit large this part. Okay. That's fine. Oh, it looks like this. You see? If I change it, I use a different way to create this y. I get y. The histograph of this y looks like this. Maybe I put the n in the front so I can change the number of the samples. And then the n now is 2000. And here, this is the n. This is another n, right? All of them, I suppose they have the same size. Then I can do some calculation, make some changes based on these three. Right? Now, by these three, I have distribution looks like this. This is the histograph of this y. You should know what is the meaning, right? I didn't explain it today, but now let me see a little bit. Like each bar, these bars, each bar give the value, give the number of y whose value close to here, like 1. Like this bar we have 300 and something, 300 maybe 310 or 20 numbers. They are value between 0 and value nearby 1, right? This is 1, nearby 1. And each bar, like this bar, they are the value close to, but almost smaller than 5, and the value will be 100 and some date. Right? Totally, we have 2,000 date. Some date between 0, close to 0, some value close to 1, some value between 1 2, some value close to 2, and so on. And here, when I draw the histograph, I didn't put how many bars do we have. Then there should be 10 bars. You see, 1 2 3 4 5 6 7 8 9 10, totally 10 bars. If you want, you can give more bars. For example, I give 20 bars. I put this 20, that means 20 bars. I have 20 bars. You see, this looks 20 bars, right? 20 bars. If I change more, okay, 30. Yeah, 30. Then even more bars. Yeah, even more bars. So you can, yeah, just normal one. It's fine. Let's keep it. Then after you get this, you can think, okay, the distribution of these y will be some kind of distribution. You see, this is not symmetrically. You cannot use normal distribution. You will change something else. For example, here you can choose. For example, you can choose F distribution or beta distribution. Yeah. So here you can say it is might be an F distribution, or even a gamma is also fine, or beta with the peak value close to 0, right? Yeah, so you can make your assumption. After you make that assumption, then you can try to estimate the parameters. Different distribution, you have different parameters and different formulas. Then similar with our homework, you can try to estimate those parameters, right? Like normal is mu and sigma square. We did this in homework, right? In our homework. And the beta, you have I and the j, you need to estimate. Gamma, you have a k and theta, you need to estimate. And f, another to n and f. And the chi square just one parameter. Yeah, chi square, both chi square and the t, they only have one parameter. Yeah, so you can try to estimate. But t is symmetrical. Chi square, yeah, chi square. Maybe this one you can also, this example you can also suppose it is a chi square distribution. Alright, okay. So this is one thing. But like this one, you have one peak here, and this place it seems like might be some peaks else. So maybe you think this is not just one distribution. Maybe there are 2 or more distributions. You can also think this one has 2 distributions, right? One peak is here, another peak is here, and another small peak is here. So for that kind of things, you can also assume this distribution is a combine of several different kind of distributions. We can work like this. Let me see. I use okay, this is one I put today. Fine. Separate. Okay. Here I give another kind of distribution. I still use x1 and 2. 1 and 2. But I use a different function, random. This function can give the type of the distribution. Like I just use normal distribution with parameter let me see, x2 I just keep it a uniform distribution between 0 and 1, and this one I suppose the mu is like 5, and I say sigma square, it is just 1, and then how many samples will be 1 row and n column. It's a totally n number, right? Okay, I have x1 and x2, and then I merge these two together. How to do it? The merge is a random way. So you think like you have a coin. Similar with our early examples, right? Consider if the histograph has several peaks, then suppose x equal to some p, not p1. Let's suppose like this. Suppose the model is similar with a coin. You think you have a coin C1 and C2. You have two coins, but not really coin right now. For C1 you have PDF F1 of x. This one you have PDF F2 of x, and you have probability to take a coin, because you have P1 probability you take C1, and the P2 probability you pick C2. It depends. Maybe if you have several picks, here's 2 picks. If you have several picks, like 3 picks, then you have the third one, depending on how many picks do you have in histograph. And then each one you have a different distribution. Then the overall thing, like this is x. So x is, what is x? X will be, you think it's a 2 steps experiment to give you what is x. Firstly, you need to pick C1 or C2. After you get C1 or C2, then you have a sample based on this distribution. Similar with the coin problem. Remember the coin problem, right? Different coin. One is more chance to get face, another one is more chance to get tail. Then you pick one, you don't know which one, you have probability to pick either one, and then you check the result, it is a face or tail, right? Now is similar thing. You have a probability, you pick some coins, but each coin give you a sample space, not just 0 and 1. Like the coin just 2 results, 0 and 1, face and tail. Now each CI is a kind of you have a kind of like PDF. You can also consider the discrete type. Then this here will be PMF. Here I just discuss PDF. Very easy. Okay. Then what is the PDF of x is? It will be this one. It is just the fx of x or equal to p1 times f1x plus p2 times f2x. Now here I just write in case we only have 2. If you have more, then you have more terms here. Right? Just look like this. It is just like this. If you want to prove, it's not hard. So things like this. We check the CDF of x. It will be probability of x smaller than x, right? This is definition of the CDF. This is CDF. I just show it. This is CDF. And what is this probability? Now we use the law of total probability. We use this law. Then it will be probability of x smaller than x in case C1 times the probability of C1 happens plus the probability x smaller than x in the case you pick the coin, that coin is C2, and then probability of C2. Okay, the first one, in the C1 case, the CDF will be F1. So this is F1, the CDF, do an integral from negative infinity to x, right? Smaller than x, all the values smaller than x. Here I use some bait, d bait. Okay, this is the probability, just this probability. Okay, this probability. And this one, we suppose it is a P1 to get C1, so this is times P1. And the second part will be similar. Integral from negative infinity to x. The density, now the density, because the C2, in C2 density is F2, so I have F2 of beta d beta times P2. Okay, PC2 is P2. Okay, this is a CDF. Now what is a PDF? PDF, it is a derivative of CDF. Okay, you take derivative of this one, you take derivative. This one take derivative. Remember in the calculus, the integral take derivative, then you go back, right? The integral and the derivative, they are appear. You do integral, then derivative, you go back. So this is just F1. P1 is constant. And similar, this one you take derivative, you get F2 of x. Then times the probability P2. Okay, so this is just I said here. Here I put P1 in front, right? Probability in front. This is in back, the same thing. Okay, so we have this one. And this one, how it looks like, the things like you have P1 share of F1 and the P2 share of F2, and add them together. For example, you have F1 and F2. Like this is F1 and F2. This is F2, right? You have 2. This is F2. This is the density function. This is x. Here the peak value occur at 10, and this peak value at 2. You have 2 density functions. Now you add them together. Add them together. Suppose this peak value here is 4, and here is like a 3, the peak value. And I have P1 equal to 0.6 and P2 equal to 0.4, right? Totally should be 1%, 100% should be 1. Now you merge them together. This one times 0.6, so where we like it's still similar like this, but now the peak value will be 1.8, right? 3.6 is 18, the 1.8, and this one is 4.4 is 1.6. So 1.6, things like that. Now you add them together, so the whole density function will look like this. You have 2. This is a fx. It has 2 peaks. Okay. So when you have a distribution, when you have a histograph, you see, oh, there are 2 peaks. Then you can imagine, okay, it will be things like you have 2 or more distributions. They merge it together based on a coin. You use a coin to determine which one will happen. And you get C1, okay, the first one will happen. And you C2, you get second one will happen. Things like that. Yeah. So now we go to here. In my example. So here I have x1 and x2. X1 is x2 will be old one. There will be a uniform distribution. The value were between 0 and 1. And the second one it is a normal distribution with 5 as the average value, is 1 as a variance, and both have same size. And now I need to merge these two together. Merge two, use a coin. So I use a coin firstly. Coin is what? Coin is also random 1 and n. Random 1 and n. This will be value between 0 and 1. I check whether it is larger than or smaller than like 5,4. So what that means? This means I have 0.4 chance C is let me see, larger than 0.4. If it is larger than 0.4, it will be 1. Then 0.4 chance there will be 0, right? So this is a logic operation, right? This is logic operation. Logic operation, the result is true that related with 1. So larger than 0.4, we have 0.6 possible it is true, and the other side 0.4 chance it is fail, it is false. It is false, then there will be 0. Okay, C will be this one. And then I use the y. Y is merge of these two, so x1 times C. So when C is 1, this is just x1, and plus x2 times 1 minus C. That means when C is 0, 1 minus C is 1. 1 minus C is 1. Then we have x2. Alright. Okay. I have this y. Then I want to see the use a different figure. Just one figure. I don't need the first one, right? If you want, you can see it. Now I just want the second one. Okay. Here's the graph of y. Y, I also use 20 bars. The histogram with 20 bars. Okay, save and run. Looks like this. The histograph looks like this. We have two parts, right? The whole histograph has two parts. One part is here. Actually, this is related with a uniform distribution, and the other side is a normal distribution. And we have how many chances we have? C has 0.4 chance to be 0. That means right here. So 0.4 chance y is from the x 0.4 chance it is 0. When it is 0, the result coming from x2 is coming from x2. Okay, you can change this value, then the distribution will be different. Alright, things look like this. So in this case, you can still estimate, but now you should know, depending on the date, just depending on the date. You look at date, you should know this date is coming from two distributions, each with certain kind of possible, so they merge it together. If you just look at the date itself, like here I have y, right? You look at the y, double click, yeah, this is y. If you look at the y, it's hard to, if you just look at the data individually one by one, it's hard to say which one is which one. You see, which one is which one? You don't know. I don't know if you look at it. But when you give a histograph, it is quite clearly, right? You have two peaks, and each one depending on different kind of distribution. Like this one, you can think the first one is where I separate it as 3. Okay, I give more. It's not so clearly, so I can give more details on the graph. For example, here I give 40 bars. F5 to run it, and the result, something wrong. Fine. Nothing changed. Yeah, change. Okay. So look like this. So the first part between 0 to 1, this seems kind of a normal distribution, uniform distribution, and this part you have a peak value. This looks like a normal distribution. Then you know this is combined of two, right? Combined of two. And okay, in this case, you can also use the moment method. For y, for x, and here I use x. Here is x. For this x, we have this e of xk. It will be integral of fx of x times the k's power of x dx, right? It is this one. Now fx is a separate of these two, so this is an integral of, sorry, I put the xk in the front. This is f1, p1 times f1x plus p2 f2x dx, right? Separate, yeah, the integral. Okay, then I can separate, right? This one is just fx, this is just fx. Now I separate, so the first part is xk times f1 of x dx, and p1 is constant, I put it in the front, outside the integral. And then the second part is similar, I put p2 outside the integral, and inside the integral it will be xk times f2x dx. So this is p1 times e of xk plus p2 times e of xk. Okay, that means we can use the moment method again to estimate parameters. This one close to but depending how many samples, right? We have this one. So we have p1 e of n of x close to x to the k as to k. We have this. So we can use this to estimate parameter. And each one for x ex1 and ex2. For x1 and here's x1 and x2. Sorry. Yeah, this is f2 according to x2, f1 according to x1. x1 and x2, like in this example, by observe this histograph, you can think, okay, x1 is a uniform distribution and x2 is a normal distribution, and then the parameter, right? Each one they have some parameter. So what are the values of the parameter? You can still use the moment method to estimate. But now the formulas you need to use this one. So this is coming from the data, right? n of xk. By the observed sample data, you can have this one. And these two, based on your assumption, you can have some parameters, like here. x1 is you think is a normal, x2 is a uniform. Normal distribution, you have two parameters, mu and sigma squared, or mu and sigma. And the second one is uniform, you have a and b. Then you can try to estimate, right? Okay, so things like that. When you have real data, before you start to give some estimation, you can check the histograph and then give you model, that model will be some kind of distribution with certain unknown parameters, and then try to estimate the parameter. Then you can have some very good description of the random variable. And of course, if you have more data, then your observation, your estimation will be better. Right? If you only have few data, less data, few data, then estimation is just, it's still estimation, right? It's even maybe not so good. You try to get more data, you have more estimation, more better estimation. Okay, that's all for today. I want to give you. Okay, then see you Friday. Friday I will give the review for the final exam. Alright. Okay. And that's all for today. See you next time. Bye bye.